Welcome back, folks. So in this video, we're going to continue our journey into how to transform functions and their graphs by taking a look at stretching and compressing. So we'll start off with vertical stretching and compressing, and just like shifting, it's pretty easy to see, I think, the vertical stretching and compressing. Just a note, when we're talking about stretching / compressing, the kind of center, if you will, of that stretch or compression is the axes. So when we talk about stretching it vertically or compressing it vertically, you're imagining that you're pushing everything closer. If it's compressing, you're pushing everything closer to the x-axis here. So if this is my x-axis, you're pushing all the negative, the points that are below the x-axis, you're pushing them up. You're taking all the points above, smushing them down. And if you're doing it horizontally, you're smushing everything towards the y-axis or pulling everything away from the y-axis. So if we talk about vertical stretching compressing first, in this example, we're starting off with, at this point, I think it might be my favorite parent function because you can show a lot of things with it, the quadratic x squared, right? And so there it is on the left side in black, and on the right side here in red, I just took that black graph and I smooshed it down. So I tried to smush it and make it half as tall, basically. And so that's what this says there, smush. I don't know if you spell smush with a U or two O's, but that way it looks funnier, so I'm going to use that. And so the resulting part is, well, all the y values get, again, squished down half as tall. And so the corresponding points here, and because it would have gone so short, I also added in -3 and 3. But this green point, -2, 4, now becomes -2, 2. And the blue point, 1, 1, becomes 1, 1/2. And you'll notice here, the point at the origin, because it's already on the x-axis, it doesn't go anywhere. It gets as smushed as it's going to get. Alrighty. And so what's happening here is that, well, we can kind of see all the y values are just half of what they were. And so I don't want to take too much time here because the horizontal one's going to take more time. Really, I could rewrite just g of x is the original f of x, right? It's the exact same value. Well, let's break it down because there's no reason not to take our time here. If I look at this green point here, this is, well, let's continue where we were. On the right side, the left side, we have -2, f of -2. Right? And on the red, that corresponding red point is -2, g of -2. So really, that g of -2 is just the same f of -2, just squished in half. So I'll take that and divide by 2. Or another way I could write it, this would probably make more sense because we can actually see the compression factor, if you will, right here. I smushed it by 1/2, and I just multiplied the y value, the original y value, by 1/2. And so really, just g of x is just equal to half of f of x. And you can imagine if I wanted to stretch it twice as tall, instead of multiplying by 1/2, I would just multiply it by 2. And so really, if you're stretching or compressing by, I'll just say by a factor k, usually we'll use k for stretching and compressing, then your new function, g of x, is just the original function, f of x, times k. You just multiply all the y values times k. And so if we do a quick little example here, we could use my maybe second favorite is x squared, or sorry, the absolute value of x. Let's graph, let's see, y. I've been using red, so let's do that. F of x equals 3, absolute value of x. And so I'll draw in here my parent function. Once again, sorry it's so messy, my parent function is absolute value of x, like so. And so now, if this point is at 1, 1, then the new corresponding point is at 1, 3. And so this one, well, we know it's also linear. So the fact that it's linear does not get changed by the fact that, or when I, stretch it, compress it, and likewise when I shift it, right? It just tell you how, if this is what it looks like originally, when I stretch it upward, it is basically going to close up. And so it's going to get stretched like so. So my slopes now are plus and minus 3 instead of plus and minus 1 like they were. Alrighty. Let's take a look at now stretching and compressing horizontally. Alrighty, so I've copied my original parent function, f of x equals x squared, and now instead of stretching or compressing it vertically, we are stretching it horizontally. So in this case, I want to stretch it out and make it twice as wide. And so every coordinate or every point on the original function gets pulled twice as far away from the y-axis than it originally was. And so that would be saying you'd be essentially doubling the x-coordinate. So this point right here, the green one, if it was at -2 before, now it's at -4 on the x. But it still maintains its same height. Be careful of that. It maintains its same height. So still -2, 4 becomes -4, 4. So I'm actually going to write that here. -2, 4 turns into -4, 4. And if I want to write it as f and g, because that's eventually where we're going, like we have been, this would be saying that -2, let's just actually write it this way, because this 4 is f of -2, and that stays the same now for g of -4. Keep that in mind, because again, the y values don't change here, only the x values change. Just like we did for the horizontal stretching, horizontal shifting. Okay, so now, and over here on the blue one, that 1, 1 turns into 2, 1. And we can see here that f of 1, the original f of 1, corresponds to the new g of 2. And here's where I was kind of going with this, is that what we want to do is we want to be able to write g as just a transformed version of the original function f, because the original function, that's a function that we know how to graph easily. Like, I know how to do x squared. And so if I can write g in terms of f, then I know what to do. So that's why I have this, that's why I wrote this last time on the shifting video as well. How can I write it in terms of f? F of what? Well, when I plug in 4, I have to trick the function f into thinking that it's plugging in 2. Or sorry, when I plug in -4, I have to trick the function f into thinking it's plugging in -2. And so what happened here? Well, what's the connection between -4 and -2? Or what's the connection between 2 and 1? The connection is right here in the stretching or compressing factor. And so when I plug in -4 for f, the way I'm going to convince it or trick it into thinking it's plugging in -2 is to divide it by 2. And I'm going to draw this in green because that's where that stretching factor comes in. Likewise, over here, I can rewrite this one as, I'll slide over here, f of 2. Now when I plug in 2 to this, into f now, I'm tricking it into thinking that's actually plugging in 1. And so I'm going to take care of that, again, by dividing by 2, like so. And so if I stretch it out, and then now by a factor of 2, what I'm really doing is I'm replacing, if this was originally f of x on the left side there, then actually the red function here is really just that same function, still f, but instead of plugging in the original x value, you're plugging in these new x values and then cutting them in half. Divide by 2. And I'm going to put that 2 in green because that's where, again, this factor of 2 is showing up in the stretching, how wide we stretched it. Okay. And now an example, or sorry, so in general, if I'm stretching it horizontally or compressing it, actually, I'm just going to write it stretching because this will make sense. If you're just stretching it by a factor k, then you're going to replace that you're going to replace x in f of x with x over k, or in other words, times 1 over k. I'll write it like that. Okay? So here's what we did, is that we stretched it out by 2. But in order to kind of, in a sense, undo that, so that it is the original function, to like kind of correct for that, you're just dividing it by 2. That might actually make sense now that I think about it in terms of why you divide by k. Okay? And likewise, if I want to squish it, compress it, then we would multiply by, say, if I want to squish it by 1/2, so the graph is skinnier now, then I would multiply it by 1 over 1/2 or multiply it by 2. And the reason that works is because, in a sense, all the x values that you're plugging in they're now appearing into the function. You're putting them in twice as fast. So let's do a quick example here. And then there's one more thing I want to talk about. So let's talk about, f of x. Let's sketch absolute value of 3x present. Oh, we'll do this one in red, excuse me. Just like we have been. Ooh. So I'm going to draw my axes here. So again, my parent function is y equals square root of x, or f of x equals square root of x, or not square root, excuse me, absolute value of x. Just now, what does this mean? Well, this would mean, if I rewrite it, I'm rewriting this as 1/3 times x. And so this would mean that I'm multiplying it by 1 over 1/3. And so my k, my stretching factor, is equal to 1/3. This would mean I am horizontally stretching it 1/3 as wide, I'll call it. 1/3 as wide. But if you're stretching it 1/3 as wide, you're actually squishing it. In other words, you're squishing it, squishing 1/3. Again, no, 1/3 as wide is really what you're doing. And so now, the way that's going to work is that since I'm squishing it now, it's going to look like this. So this point right here, if this was, let's pick this point right here, 3, 3, then that's going to go to, you're going to shrink the x value by 1/3 to 1, 3. And likewise on the negative side here. You might notice that this actually looks exactly the same as the vertical stretching here. Now, that just depends on the graph. Okay, you can see here, actually, on a parabola, horizontal stretching and vertical stretching, compressing, are the exact same thing. But that's not always going to be the case. Here's what I mean by that. You could get the same effect of squishing a parabola downward as stretching the original one. And likewise, if you squished it vertically or horizontally and make it skinnier, that'd be the same thing as taking it and stretching it out. But notice this. When I smushed it to half its height versus stretching it twice as wide, those ended up being different graphs. And again, this is a result of the function. Okay? And so I just want you to be careful of that. In some cases, a horizontal stretch compress and a vertical stretch compress can achieve the same thing, but it's not always the case, and you have to be really careful of that. Alrighty? Hopefully this video helped, and we'll do one more video talking about reflecting, which is not actually too bad. Alright, catch you then.